Hey, welcome back to Mr. PLS with PreCal. This is Unit 1, Topic 1, Lesson 3, as we explore piecewise functions. Start off with the warm-up on square roots. So we're going to list out all the key characteristics of them. Square root, remember, these are the functions that look like this. They have an endpoint, no asymptotes, so that kind of answers some of those questions. So the domain for the parent function would be x is greater than or equal to 0. So it starts right here on the x-axis. Anything to the left is undefined. The range is everything above 0, so it's y is greater than or equal to 0. This is bounded below because the entire function is above this horizontal line. It's increasing the entire time, so that's when x is greater than or equal to 0. It's never decreasing, and it is not symmetrical. It is not an even or odd function because there's no reflection over the y-axis or the origin. It does have a minimum, and it has a minimum at 0, 0. Now, quadratic functions look like this. They are parabola shaped, so the domain for the parent function would be all real numbers, and the range would be everything that's above or equal to 0. So because it's everything above that line, which means it's also bounded below. So it's bounded with the lowest point, which means it has a minimum also at 0, 0. It is increasing when x is greater than 0, and it's decreasing when x is less than 0. Symmetrical, this is an even function because it's a perfect reflection over the y-axis. Okay, so as we get into a piecewise, so a piecewise is basically a function that's made up of multiple pieces. So when you look at this function right here, what I see is two different pieces. I see a quadratic piece, which goes to right here. It's like the left side of a parabola, and then it becomes a trigonometric piece, which happens to be a sine piece. So this is a sine with a connected to a quadratic. All right, so I look over here and I see three different pieces. So I see a greatest interval, or a step function, greatest interval function. Meaning that the whole is on the right-hand side, or least interval if it was on the left-hand side. And then I see absolute value, and I also see square root. Square root just like on the warm-up. For this one, I see linear, or I guess you could say this could be absolute value. It could be the left side of absolute value. So I'm going to say linear because it would be easier, though. And this would be a logarithmic because clearly it has a vertical asymptote. This would be a square root. It just happens to be facing to the left. And this piece right here, it's actually kind of hard to tell. I'm going to assume it looks like it's quadratic. Because you can see this parabola shape right here, and then it stops right there. Okay, so now we identified what a piecewise function looks like. Now we're going to be able to write them and be able to discover some information with using limits. Label each of the pieces. Let's come up with a piecewise function. So we're going to look at these three pieces, so green, yellow, and orange, and each one's going to be a different piece. Now, the green one makes a parabola. Actually, that's x squared. So this is x squared. This is a straight linear piece, which will just be y equals x. And the orange piece over here, I know it's kind of hard to see, but this is a cubic function. This is y equals x cubed. And the reason I know that is because 1 cubed is 1 and 2 cubed is 8. And that looks pretty close, like it's going to be about 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's going to hit about right there. We're in pretty much in the vicinity. So we now know what the equation is for all three pieces, so then we can write them. So we know the equation is x squared when the domain is less than -1. So when x is less than -1, because that's this piece. Now there's a solid dot right here, which means it's included in the second piece. So we know the graph here in the middle is x, and that's when x is between -1 and +1. So anytime x is between these two numbers, which is in the yellow portion, then you know that this is the equation. And then the last piece, which is x cubed, is when the domain is greater than or equal to, I'm sorry, just greater than, because I've already said or equal to. I could have put the or equal to here instead of here. It doesn't really matter in this case. I'm just going to put it one or the other, though. So it's when it's greater than 1. Why do we need an open circle in the first place? So open circles here, and the reason why we have that is because we don't want any one place, any one domain to have two different ranges, because if that's the case, then it is no longer a function. And it very well states that this is a piecewise function. So it has to be open on one side and closed on the other, because only one of them can be the answer. Why can't include an equal sign for the last constraint? Actually, as I think I already mentioned that earlier, so it can be done that way. You just only want to have it on one or the other. Try to graph the following piecewise functions. Where do you begin? Okay, so start by, we're going to use a function table for this. Now, I know you can use your graphing calculator for this as well. So I'm going to start with a constraint, which is anytime x is less than or equal to -2. So I'm going to start with -2. And it says anything less than that, so it could be -3 and -4, and I'll stop right there. So I'm going to use this first function table for the first piece. So if -x squared is the equation, so I put -2 in for x, -2 squared is 4, and the opposite of 4 is -4. And then if I put -3 in, -3 squared is 9, and the opposite of that would be -9. Put in -4, -4 squared is 16, the opposite of that would be -16. Now, I don't know if all those pieces are all going to fit, so I'm going to change colors here. So -2, -4, 1, 2, 1, 2, 3, 4. And that is an or equal to, so that I'm going to use solid. -3, -9, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to go like this. Remember, it's quadratic. All right, changing back colors. So I'm going to do the next piece, which is an absolute value, and then this time it's from -2 to 1, but it's not including this. So this one was including, and this one's an open dot. So this one is from -2, so it could be -2, it could be -1, it could be 0, or it could be 1. So those are all the possibilities. So if I put -2 in there, absolute value of that would be 2. The absolute value of 1 is 1. The absolute value is 0, 0. The absolute value of 1 is 1. If I plot those points, I'm going to use a different color this time. -2, 2, open circle. -1, 1, 0, 0, and 1, 1. So there's your pieces, and then it's closed on the other side. And for the last piece, so this time it's linear, so it's anytime x is greater than 1, not or equal to, so we're going to start with the constraint 1, 2, 3. If x is 1, x is 1, x is 2, x is 2, x is 3, x is 3. Okay, pretty easy. And 1, 1, so it's in the same place, but it would be an open circle. 2, 2, and then 3, 3. So it connects like that. Okay, so is the function continuous at x equals -2? So no, it is not. You can clearly see at -2 there's a jump here. So there's a jump continuity, and explain why or why not this with limits. Okay, so I'm going to use limits. So I'm going to say the limit of, let's see, so as x is approaching, so the first piece is -2. As x approaches -2 from the left-hand side, so the limit of f of x is, and now we're going to figure this out. So from the left-hand side, which means I'm using the first piece, and that's what that negative sign is right there. If it was a plus sign, then it means it's from the right-hand side. So if I put -2 in here, I've actually already done that. I get -4. Now, the limit of f of x approaches -2 from the right-hand side, which means I'm using this function right here. So if I put that -2 in, I end up getting an answer of 2. Now, clearly I'm getting two different answers because I'm using two different equations. And, well, that doesn't always mean that case, because actually right here you get the exact same answer, which tells me that there's jump continuity. So that's proving it. Is the function continuous at x equals 1? So yes, it is. And the reason why is because when you do the same thing, you're going to get exactly the same answer. This answer and this answer happen to be the exact same. So that is continuous. Okay. So number 2. Let's see. Very similar to the last question I just did with some evaluating down here. So there's three different pieces. So I have three different function tables. If x is less than 0, so I'm going to start with the restriction. Start with 0. Anything less than it would be -1 or -2. So if I put these numbers into this equation, put 0 in for x, I get 0. Put -1 in for x, I get -1. And okay, so it's really just x. And for the second piece is from 0 to 1. So 0, keep in mind this is an open circle because it is not or equal to. And this one is a closed circle. 0 to 1 would be 0 and 1. That's it. And if I put 0 in for... Okay, so during this, if I put 0 in for x, there is no x, the answer is 0. So the answer is 0 no matter what. And if x is greater than or equal to 1, so start with that, it's going to be greater than or equal to 2, 3, and so forth. So it's x minus 1. So 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2. All right, so now I'm ready to plot these. 0, 0, -1, -1, -2, -2 with an open circle. Let me start that over again. So... open circle at 0, 0, -1, -1, -2, -2, connect it like that. So there's your linear piece. Then it becomes the answer is 0 from 0 to 1. So now that closes up the circle because of that. And then 1, 0, and 2, 1, and 3, 2. All right, so all linear pieces. And there's your answer. So it says evaluate the function. So the key to evaluating the function is the fact that I have to first determine which piece I have to use. So f of -2. So I look at the restrictions. I see that -2 is less than 0. So -2, I put that in for x, and I get -2. First, I need to figure out which piece f of 1 is. F of 1 is in this constraint because it's or equal to. So 1 minus 1 is 0. F of 0 would be in this constraint, middle constraint. So that means the answer is 0 because anything in this range is 0. Keep in mind it could be decimals. And f of 100 would be in the last one, and 100 minus 1 is 99. All right, so due to lack of time, because I'm already at 12 minutes in this video, I'm going to skip through these two questions. They're very similar. When it's -0.5, just keep in mind that -0.5 is in this constraint. So -0.5 is the absolute value of that, which would be 0.5. And on the last one, so we're writing a piecewise function. I might only have time for just one of these. So write the piecewise function of the first one, and keep in mind there's two pieces. First, I'm going to write what the equation is. This entire function is at a height of 1, and that's when x is less than -1. And this is a quadratic piece, so that's x squared minus 3. And that is when x is between, well, actually, x is greater than or equal to -1. So that entire time, and it goes infinitely to that direction. Actually, looks like I have enough time to finish this last one as well. 2 minutes left. First piece is quadratic, so it looks like a parabola. So that's x squared when x is less than or equal to 0. And the other piece is a square root, so that's square root of x, and that is when x is greater than 0. Keep in mind you don't want to put or equal to on both of them. All right, thanks again for watching, and please look forward to future videos. Have a great day.